This is the view to the east from the edge of Bodmin Moor. It's rich lowland farming country, a patchwork of cultivated fields and woodland. But as we turn westwards, mounting the steep edge of the elevated moorland, we come to a very different landscape. On these broad highlands, there's very little farming and few trees. The vegetation's mainly poor grass, bracken and gorse. In the broad, shallow valleys, reed beds indicate the presence of marshes and peat bogs. Landscape and geology are linked, and contrasting landscape features often indicate differences in underlying geology. We'll show how the landscape in this part of Cornwall relates to the underlying geology, and then use similar relationships between geology and landscape to trace the extent of a large geological structure in Dorset. On Bodmin Moor, the underlying rock is close to the surface. The hillsides are littered with boulders, and the hilltops are crowned by outcrops of solid rock known as tors. This is the Cheese Ring Tor, and below it an old quarry shows that the rock extends to depth. Bodmin Moor has been quarried extensively, and to see what the rock is like, we'll visit a quarry on the west side of the moor, where the rock's still being cut and polished. This is the rock that underlies the whole of Bodmin Moor. Let's have a look at it a little more closely. It's a totally interlocking mosaic of crystals, and they're about 1 to 5 millimetres in size. So it's a coarse-grained igneous rock. And the minerals themselves are milky white feldspar, glassy grey quartz, and very dark brown biotite mica. So it's a granite. In fact, it's the same granite that we sent you in the jiffy bag. But this specimen doesn't tell me any more than your little hand specimen would. So let's go into the quarry to see how it looks on the quarry faces. Well, this is where the granite blocks are actually being quarried. Now, you know that granite has crystallised from a magma, so you'd expect the rock to be fairly homogeneous. But in fact, within the granite body, there are natural lines of weakness called joints. This plane in front of me here is a joint face, and here's the one perpendicular to it, running in this direction. And there are two roughly horizontal joints here, about 1 metre apart, and this pattern is repeated throughout the quarry. In fact, if you look on the other side of the quarry, the two smooth faces are joint faces. And these joints are very important because once the granite has been exposed on the surface, the main access into the body of the rock by weathering agents depends on the joint pattern. But we can see that better at the Cheese Ring. Well, this quarry hasn't been worked for a very long time, but these blocks are much the same as they were on the day that they were quarried. Apart from some lichen growing on them, they've hardly been attacked at all. That's because granite is a very hard and resistant rock. You can see in this little puddle in front of me here that water doesn't penetrate into the body of the rock at all. But where there are joints, these assist the water in getting into the rock by increasing the surface area. So, in the face above me, you can see vertical and horizontal joints picked out by the grass. And the water can get in there so that weathering can begin. And towards the top, you can see that small blocks are being broken off. And it's at the surface that you'd expect weathering to begin and a soil profile to start. When the granite breaks down, it forms particles about the size of the constituent crystals. So that's about 1 to 5 millimetres. So it's a sort of coarse gravel. But it's a very thin, infertile soil, devoid of plant nutrients. And so it's only tolerated by species like heather, bracken, gorse, and pretty poor grass. The characteristics and features of the moor are determined by the underlying granite, which is hard, resistant and impervious. The edge of the moor is marked by a steep slope, and this coincides with the edge of the granite. But looking to the land around the moor, you can see that the landscape is quite different. There are fields here, and it's obviously good farming country, and we can imply that the rocks underlying the farming country are different from the granite. So let's go and have a look and see what the rocks down there are like. These are the rocks into which the granite intruded. Originally they were laid down as sediments, muds and silts in the Middle Devonian age. But because of the heat of the nearby intrusion, they've been turned into slates. Now the slates are relatively softer than the granite, and they break up by splitting much more easily than the granite does. And this actually helps in the formation of small particles from which a soil can develop. So this explains why the lower land is the farmland. It's developed a much better soil than has the granite. Well, now we can summarise what we've seen so far in this programme. The granite is hard and resistant to weathering, and it stands out as a positive landscape feature, and the edge of it is quite steep. The lower land, on the slates, the country rocks, are softer, and they've weathered into a decent farmable soil.
This Dorset landscape looks quite like the Cornish lowlands, but here the underlying geology is quite different. Local building materials often provide a clue to the underlying geology of an area. Widespread use has been made of two local limestones, the Portland and Purbeck stones. So we may expect these limestones to form an important part of the underlying geology. From low down, it's difficult to make out any pattern to the landscape, but from a higher vantage point, looking east, you can see that these hills form a distinct ridge that curves away to the southeast to form a flat-topped area that's cut by cliffs at the coastline. This headland's called St Albans Head. Here the cliffs provide us with a slice through the landscape where we can examine the underlying geology and see how it influences the topography inland. The rocks capping these cliffs are showing good horizontal layering, that is, they're bedded, so they must be sedimentary in origin. And they're also cut by vertical joints. Well, there are two kinds of rocks surrounding me here. There's these blocks that have obviously fallen down from the capping on the cliff top, and this grey material, which is very loose. It comes away very easily when I use the hammer. It's very dry at the moment. If we'd come here in the winter, this would have been rather soft and plastic. I could have moulded it in my hands. It is, in fact, a clay. Well, what about these harder blocks? Rather harder than the clay. Let's have a look at it with the hand lens to see if I can work out what it is. Well, there are a lot of little, very small rounded particles in there, and also some shell fragments. And I dare say if we look around on the fallen blocks here, there'll be quite a few fossils and fossil fragments showing up. So it looks as though this is a limestone. It is, in fact, the Portland limestone. Even if it hadn't had the shell fragments in it, there is a very useful test one can do just to check that one is dealing with a limestone, and that's to use dilute acid. Well, the fizzing is produced as carbon dioxide comes off from the calcium carbonate. So basically we've got two rock types here, the softer clays, and they're overlain by the harder Portland limestone. And this sort of situation commonly develops a process called mass wasting. Imagine these clays in winter when they're highly waterlogged with rainfall and spring water coming out of the limestone. They're very unstable, and they're made more so by the fact that erosion is taking place at the foot of the cliff. And so periodically, great masses of clay slip off and slide seawards. So there's a grey scar of clay where a huge block has slid towards the sea, and there it is down there. And the top of that block is rather flat, it has lusher vegetation on it, indicating that it's rather waterlogged, and it's inclined towards me slightly. So that got down there by a downward, slightly rotational movement. And from time to time there are huge landslips like this along these cliffs, and they undermine the Portland limestone. Well, an excellent way of summarising the kind of geological information we've just been looking at is to do a field sketch. Now here I've sketched in some of the major elements of the view that we can get from this viewing point, which is above the cliff we've just been studying. So at the top of the cliff, as we saw, is the limestone, the Portland limestone. And as you go down, in fact, the colour changes slightly to a more grey colour, and I would think the boundary of the limestone is about here. So I'll put that in red and shade it. And then going on down the cliff, there are a couple of steps with that lush vegetation on, which, remember, mark the position of former landslips. We were on the lower one, down here. Well, what about the cliff line over in the middle distance there? That cliff is called Houndstown Cliff. It's rather more eroded. The sea is cutting away at the bottom of it, so much more of the clay is exposed. But as you look up that cliff, there is a distinct colour change about 5/6 of the way up towards the top. So in other words, we can see this layer of Portland limestone again. So I'll sketch that in. I should think that runs about there. So in that direction, in a roughly east-west direction, it looks as though the limestone is horizontal, almost horizontal, perhaps a couple of degrees inclination on it. And in this cliff just in front of us, it's horizontal as well. So we can be pretty sure then that we have a horizontal slab of limestone covering this area. So where does it go inland? Well, look across there. There is some woodland capping that hillside to the right of Houndstown Cliff. And it's pretty likely that it's woodland because it's growing on the Portland limestone, on the steeper slope. And the farmer there is using the gentler slopes of the clay as pasture land. So anyway, postulating that it's horizontal everywhere, we can dash in the boundary between limestone and clay. The difference in level here is, of course, due to perspective. It hasn't been shifted downwards. Well, further over to the left, to the west, is a headland jutting out towards the sea, but it doesn't actually form a high cliff. That's Swire Head. So where does the Portland limestone go there? Well, on the south side of the headland there is a break in slope, and it's very tempting to suggest that that marks the boundary of the limestone. So again, we can dash that in around that hillside. And notice what a flat top that hill has. It really does suggest that there is a very gently inclined, almost horizontal slab of limestone covering this whole area. And in the past, it must have been cut into by rivers. It is still being cut by streams to a very small extent today. And so there is a valley between Swire Head and Houndstown Cliff, and then another valley between Houndstown and the cliffs we were looking at. So this vast limestone plateau has been eroded both by the sea, producing the present-day coastline, and by the rivers, which have cut these steep-sided valleys. What happens to the limestone beyond and inland of Swire Head? To the north of Swire Head, the topography changes from the flat-topped appearance we observe behind Houndstown Cliff to a narrow ridge. This is the ridge we observed when we looked east towards St Albans Head. On a model, it's particularly easy to see the continuity of this ridge and how it's related to the limestone plateau inland. Inland and to the west, the ridge curves round. Eventually, it's cut by the sea to form a line of cliffs. This is Gad Cliff. Like the cliffs at St Albans Head, these cliffs are composed of massive bedded limestones overlying softer clays, so we can be certain that the limestone also forms the ridge inland. But here, the limestone's no longer horizontal. It apparently dips gently down towards the left, that is, towards the west. Still further to the west, the sea has breached the limestone cliffs to form Warbarrow Bay. And here we get a three-dimensional view of the bedding, and the promontory of Warbarrow Tout clearly shows that the true dip of the beds is steeply down to the left. That's to the north. Now I'm sitting on the north side of the Tout, and beneath me is a very steep slope. Now at the foot of it we can see bare rock. Here we're looking east, so the beds are dipping very steeply at about 45 degrees to the north. So we can say that this slope, even the grassy covered part of it, is a dip slope, because the slope itself is controlled by a single bed of limestone. Well, from here we get a marvellous view of the broad sweep of Warbarrow Bay and the cliffs behind it. And the cliffs give us a good opportunity to see yet another succession of rocks. Well, here I'm actually sitting on what are called the Purbeck beds. They consist of an alternation of clays and limestones. We saw one of the limestones making this dip slope beneath me. Now remember the dip. It's dipping steeply north, and so were the Portland beds. They're back off behind us. So that means that the Purbeck beds are lying on top of the Portland beds. Now what about the sediments over there in the cliff? They're sands and clays, and they're much softer than the Portland and Purbeck beds. But they too are dipping down to the north. So it means that as we go to the north, we're getting on younger strata. Now, as you follow the cliffs round, the variegated colours of the sands and clays are replaced by a rather pure white. And that white is an outcrop of limestone. It's the chalk, which is made up of very fine-grained remains of floating organisms. Well, let's summarise the succession of rock types we've seen so far. To do that, we use what's called a stratigraphic column, and I've sketched one very crudely here, using fairly standard symbols that geologists always use and understand. At the base of the succession, here, is the series of grey clays that underlie the Portland limestone. Then, of course, there is the Portland limestone itself. Here's a sample of it. And then above the Portland limestone come the Purbeck beds, the alternation of clays and limestones. There's a huge variety of rock types there. I've chosen this one. It's called the Purbeck marble, and it's used as an ornamental stone in many churches throughout the country. And then there's a thick succession of sands and clays. Here's one of the sands, a very coarse variety, almost pebbly. And then finally, on top of those sands and clays, the chalk. Now, what's interesting about these rock types is that only the Portland stone, and to a lesser extent the Purbeck beds, and also the chalk, they are the ones that are resistant to erosion, whereas the grey clays and the sands and clays are much less resistant to erosion and so tend to form hollows in the topography. So we can relate this stratigraphic column to the topography of this region. Well, first let's get rid of the rock samples, and I'm going to turn the stratigraphic column over on its side so that the order that we'd go through the rocks in that direction is the same as we'd meet them going round the bay. So that means that the chalk up here is now on the north side. Well, the kind of topography that the rocks express themselves at is like this, with a ridge formed by the chalk, and then lowland over the sands and clays, and then another ridge formed partly by the Purbeck beds but mainly by the Portland limestone, which has a rather steep southern slope, and then lowlands again over the clays. Now, both these ridges have dip slopes, in other words, slopes developed in the same direction as the beds are inclined. And they also develop on this side what are called scarp slopes. So the chalk has one there, the Portland limestone has one there, and the scarp slopes are on the up dip side of the inclination of these limestones. From the air, it's clear how the two ridges of more resistant rock dominate the landscape to the east of Warbarrow Bay. Let's return to the model to summarise what we've seen so far. The ridges are formed by the more resistant rock types, chalk to the north and Purbeck and Portland limestones to the south. Between them is a succession of softer sands and clays, and to the south of the Portland limestone occurs grey clay. The wider relationship between the topography and the geology is more obvious if we give each rock a different colour. To see what we can deduce from this relationship between geology and topography, that is landscape, let's start by concentrating on the Purbeck and Portland limestones. Remember what we saw at Warbarrow Bay. Here the Portland and Purbeck beds dip down steeply at about 45 degrees to the north. But in the area around St Albans Head, these beds are almost horizontal. So we have almost horizontal beds in one place and steeply dipping ones in another. So in between they must be, to put it crudely, bent in some way. As well as being mapped on land, these rocks have also been mapped under the sea, and if we add this information, a clear pattern emerges. We know that to the north, the Purbeck and Portland beds dip steeply towards the north. Combining this information with their horizontal orientation near St Albans Head and the offshore outcrop pattern, this suggests that they've been folded upwards into an anticline. In fact, it's an asymmetric anticline with a steeper northern side. Of course, all the other rock units would have been similarly folded at the same time. Erosion of this anticlinally folded rock succession has produced the present-day landscape of this part of Dorset.